Welcome back to the Natural Language Processing Learn from Scratch lecture series. In today's video, we'll be looking into the distributed representations. So previously we saw basic vectorization approach and many of that. We'll quickly have a recap of those and then move on to this distributed representation. So a quick recap. So what did we see in the previous video? We saw what is text representation and then saw why is it needed and what are the four different approaches in brief. That is the basic vectorization, and then the distributed representation, and then universal language representation, and then the handcrafted features. These four different approaches, we saw that in brief, and then we took one particular approach, the first approach, basic vectorization approach, and then saw many techniques under it. So what all did we see? We saw the one node encoding with implementation done, and then the bag of words with implementation done, and then the bag of n grams with implementation done. And then we saw the TF-IDF, term frequency, inverse document frequency, along with their implementation done. And then we also saw the basic disadvantages with all of these approach, right? So we saw the major disadvantages here. So what are those major disadvantages? There are mainly three. The first one was all of these techniques assume that the symbols are discrete. So it's a discrete representation. So they don't capture the real relationship between the words or the symbols. They don't capture the relationship between them or links between them. Instead, they capture them as just symbols, discrete symbols. Fine. So that is one problem. That is why it's not a perfect language representation or text representation. Second problem is the high dimensionality and the sparsity. So what happens with growing vocabulary size? In here, in the implementations, we saw vocabulary size of just 8 or 7 or 6. But then in the real life, the number of vocabulary words in the whole vocabulary corpus list would be more than a million, or could be even a lakh, maybe 100,000. So the number of elements in the numerical vector for each sentence would be huge, right? For all of these different sentences, like for bag of words, for a sentence will be representing using the vocabulary vector, and that vocabulary vector will have 100,000 elements, and most of these elements will be zero. Why so? Because in a sentence, the number of words could be 10 or 11 or even 100 or even 1,000. So only 1,000 out of 100,000 elements will be given some numbers, and that too those numbers will be given for words as per their vocabulary order, and it will be sparsely given. So there will be a lot of zeros and very few number of ones. So it is sparsity which is very much difficult when it comes to computing that for optimizing the weights of the model. If you're inputting this into a neural network, then it will be much difficult to optimize the weights, as because most of the values are zero here, few of them are one. That is one issue. And even if you give it to the machine learning models, again, getting the error and then optimizing it would be a little difficult. So, and that too, along with this, we have the dimensionality. The dimension itself is like 100,000. With the high dimension based vectors, computing cost will be much higher. So that is one major issue. And the third most important aspect is it cannot capture any of the out of vector words. So if there is a unique word in a particular document, if there is a new word in a particular document, it will simply give a numerical vector with everything as zero, because it has not seen those words in the vocabulary corpus that it has. So it will just give a zero vector, which is not correct. We have to have some kind of measures to handle the words which are out of vocabulary, right? So these were the main three issues that we faced with the basic vectorization approach. So we had to come up with a better technique, right? So that is why we went for this distributed representation. So there's a difference. So all till here, I'll even portray this as well. Wait a minute. So both of these techniques, that is the hard encoding and then bag of words, these both were symbolic or discrete representations, right? Discrete representations. And what were these? The bag of n-grams and TF-IDF, these both were distributional representations. I've already gave it. I've already given the spelling there already. So it's a distributional representation. We saw it before. So this is discrete representation, and these two are distributional representation. So from evolving from distributional representation, we got to a point where we came up with this approach called the distributed representation. Fine. So in distributed representation, we directly use neural methods to train the model to come up with the perfect embedding or a numerical vector for representing a text. Fine. So mostly these vectors were low dimensional. That is one advantage, and they were they were dense, meaning they were non-zero values. We'll look into all of this, but then before getting into the distributed representation, we'll just see some main terms to understand, like the distributional similarity. Fine. So what is this distributional similarity? So observe this image. So NLP rocks is a phrase someone is saying. Okay. So what does this rocks mean here in the sentence? It means something positive, right? Something amazing or something. Like it is changing. The meaning of the word is changing with the context of its present in its sentence, in a sentence, right? As per the context of a sentence, the word's meaning changes. So this is most important thing, because this is the most important aspect of language, and we had to somehow capture this. So what does this distribution similarity says is the meaning of a word can be inferred from its context. This is connotation, as opposed to literal meaning, that is denotation. Denotation is literal meaning, and connotation is the inferred meaning from the sentence, right? So this kind of distributed similarity is there for a same word. For a single word, there could be a distributed similarity. So the context of the word would actually change with respect to its distribution in the sentence, or its usage in the sentence. Fine. So that is the first term that you have to understand. So this is distributional similarity. And then we have the distributional hypothesis. So what is this? So in linguistics, the distributional hypothesis states the words occurring in similar contexts have similar meanings. So observe the sentence: the dash chased the cat. It could be either the dog or the cat, right? So both of these can be used in the sentence. So the usage of these two words are similar with respect to the sentence, meaning these two words have some kind of similar context, and that is what this is saying. So the distribution hypothesis states that the words occurring in similar context, they both are occurring in similar context, have similar meanings. Yeah, similar meanings, but then it's not exact meanings. So, and then their representation in the vector should be a little more closer than other words. For example, if there is another word called human, and that particular word should be kept a little distant away from this dog or cat, or maybe say chat or pencil. All of these kind of words should be kept away from the dog or cat representation in the vector space. The vector space is could be two-dimensional, or even actually it's not two-dimensional. Most of these vectors that you saw, their representation is more than 5 or 10 or 6. It depends upon the vocabulary corpus, right? We saw that for the previous approaches. Here, the low dimensional embedding could be around 100. So 100 numbers would be representing the same word. So it's a 100 dimensional vector space. So it'll be represented in that way. And the similarity between these two words would be inferred with the distance between those two different word embedding vectors. Fine. So this is the distributional hypothesis. Fine. And now we go for distributional representation. And this is where all of the different methods that we saw in basic vectorization comes into play. That is the bag of n-grams and the TF-IDF. See, all of these are actually examples of distributional representation. Why so? They use statistical techniques and use a way to say whether how well a particular word is distributed in a document. What is its frequency? How many times is it being used in a document? Or how many combinations of words? How often does a combination of word comes into play in a sentence or a document that could be given by your bag of n-grams? And TF-IDF gives number of times a particular word is being used in a particular document, and how rare is the word with respect to the document and the whole document corpus. So these kind of different metrics or the ways of representing the text could be known as the distributional representation. And they use high dimensional vectors from a co-occurrence matrix with equal dimensions equal to the corpus vocabulary. So co-occurrence matrices. So what are these? So it says how frequent a word occurs along with another word. So the bag of engrams says that, right? How like it consider, but then it's symbolic. The main difference between distributional representation and distributed representation is this. Distributional representation considers each combination of strings as a single entity. So some group of words would be considered as one singular entity, and then the number of times this group of words comes together exactly in the sentence, that would be counted as one and two, and they'll be counting it like that. Like exact deterministic match should be there between the group of words, like the grouped words as single entity and sentence. Only then the count would be increased. So that is one disadvantage, but then that is what is your distributional representation is. Fine. So you can see here as an example. So words are represented by high dimensional vectors based on the context they appear in. Yes. So it's not the context. I would say it would be just a word in terms of in bag of engrams, it would be the word order. In TF-IDF, it's the frequency. Fine. So it depends upon the metrics, but then in general, distributional representations capture the statistical features or co-occurrence, that kind of features of they use that as a metric for representing the words in the vector space. So yes, now we'll move on to our distributed representation. Fine. So based on the distributional hypothesis, distributional representations yield high dimensional sparse vectors that are computationally inefficient. So based on this distributional hypothesis, what was this? We saw it here, right? So words that are used in similar contexts could have similar meanings. Based on that, distributional representation yield high dimension. So based on this hypothesis only, we came up with this distributional representation because we want to have the understanding of group of words, how they occur together, and that kind of similarity we wanted to capture. But then we consider it as symbolically, but then that was one of the ways we followed to get the understanding of or infer the co-occurrence of words. So though we were able to come up with a representation for it, it was having high dimensionality and then it was sparse. It was producing sparse vectors, meaning there were a lot of zeros and very little number of ones or actual valued elements in the whole numerical vector. So to resolve this issue, we came up with this distributed representation scheme that compressed these vectors into compact, low dimensional, dense forms. So these distributed representations are compressed vectors, which are compact, low dimensional, meaning it need not have 1,000 or 100,000 elements in its vector in its list because of the vocabulary around. Though if even if you have 100,000 sorry, 100,000 vocabulary words, unique words, even in that case, you can use this distributed representation so that you can reduce it to just 100 element based vectors. How so? Because you won't, in many of these elements, it will not be zero. It will be dense forms. What is dense? What are dense forms? Non-zero numbers. It could be decimal numbers, positive or negative. Fine. So it will be directly. How do we get these distributed representations? We use neural networks for it. So a particular word would be given in. This be hidden layers, and it'll be processed, and then you map it with the same words. Here, actually, it's given as a picture, but then the picture will not be given. The words, words itself will be given here, and then we'll match it with the words so that we can train the neural network to represent the same words. It's almost like an auto encoder decoder kind of architecture. But then here we're specifically using it so that the words are properly represented by numbers. Fine. And if we do all of this training properly, then you'll be getting this kind of this is an example of words with two-dimensional numbers. So you'll get something like this. if you are using a two-dimensional um, vector vector representation, distributed representation. So the words which are similar to each other will come together, like tulip and rose are flowers, they come together. Lion and tiger are little similar, so they come together. Maple and oak are parts of the plant, and so they'll come together. Frog is a different thing, it'll go away. But then cat and dog will be coming together. So these kind of similarity in the vector space itself can be observed with this distributed representation. That is a major advantage. The next term that we'll be looking into is the embedding, the term embedding. So, in layman's terms, if I have to brief you, I could just say this: embeddings transform text into vectors of numbers, where vectors represent a piece of text, right? So it's very much straightforward. But then, if you have to go in detail, embeddings could be a mapping between the distributional vector space and the distributed vector space. So in the distributional vector space, the whatever numbers we have are of are resulting from the techniques like one-not encoding or bag of words or term frequency, inverse document frequency, those kind of techniques, right? But then in the distributed representation, you use a neural network, and then you use all of the words representation, all of the words that are nearby between the words for a particular word. We distribute the responsibility of representing this word with other words which are there in the same sentence. That is why it's called distributed. Fine. So in the distributional, it is just one word. If you're coming up with a vector space for one word, we'll just concentrate on just one word. How often is this word present in a document? Like using these terms like the frequency and the inverse document frequency, those kind of terms we use for identifying the statistical distribution of the term, the word itself, and then come up with a metric, a number form to represent this that particular word itself. But then in the distributed representation, we just don't take one word, but then we take all of the other words that are there in the same sentence, so that we give the responsibility of representing this particular word to all the other words also, so that the relationship between the words can be captured. And that is the main inference of difference between the distributed and distributional representation. Fine. So embeddings is just a mapping of distributional vector space, that is your one-hot encoding or TF-IDF kind of metrics, those kind of vector space, to the distributed vector space, that is using your neural networks and using a lot of different words in the sentence. Fine. I hope you understood now. So then we have something called as vector semantics. The next term is vector semantics. This is a particular approach which includes all of the NLP techniques that are used for getting the meaning, uh, lexical meaning of different words through numbers itself. So we are trying to capture the meaning between the words, the links, the relationship between the words using these techniques, and that approach or that technique would be called as vector semantics. So usually they represent, using this technique, you can get a vector of a higher dimensional space, but then even if it's higher dimensional, it will not be like 1 lakh or 100,000. Instead, it will be 100 or 500, maximum 500 dimensional space. So it could be your vector semantics, but they capture even the relationship between the words, the meaning of the word with respect to the phrase in which it is used. Those kind of interlinks can be understood, can be captured using the techniques that are there in vector semantics. Fine. So now I think you have got an understanding of all of the terms, important terms that we need so that we can understand the distributed representation. Fine. So we started off with this distributional similarity, where the word's meaning itself will actually vary with respect to its placement in a sentence. And then we have the distributional hypothesis, where a similar occurring word could be considered similar meaning word. So that is the distributional hypothesis. And then distributional representation. So here we use the statistical distribution of a word in a corpus and or in a document to come up with vector representation. And in the distributed representation, we give out the responsibility of representing one word with the other words in the same sentence, so that we come up with we capture the relationship between this word and the other words using neural networks. So that is distributed representation. And then we have the embeddings. So that is exactly the mapping between the distributional vector space to the distributed vector space. So distributional meaning TF-IDF, what are encoding, and distributed meaning your actual uh, word embeddings. Fine. And then vector semantics. So it includes all of the different approaches or techniques in the NLP domain, which enables us to capture the meanings between words with respect to the phrases where they're coming up in, and those kind of semantics can be captured using these techniques. And usually they are of higher dimensions, meaning it will be around 500 or 100 kind of dimensions. So this is how it is. So they represent like, yeah. So how are they able to capture the meaning? By making sure that the vectors that have similar meaning, by making sure the vectors with similar meaning are closer in the vector space. So through that, we can surely say that vector semantics are playing their part. Fine, fine. So now we'll move on to the word embeddings. So we saw the word to vec how it works. Right? We just saw like no, not. We didn't see the full overall fledged, but then we got an inference of how this distributed representation actually takes place. Fine. So if you extend that and properly do it for each and every word, you get this word embeddings. So word embeddings are dense vector representations of words that capture the meaning based on the context at which they appear in. Context with which they appear in. Fine. So they are built on the distribution hypothesis, that is, words used in similar contexts tend to have similar meanings. So this is the main hypothesis they use, and they also take the distributional similarity into consideration, and other uh, distributed representations main idea also in consideration. So if we see the key features of word embeddings, one main advantage is they are of low dimension. So even low dimensions between 50 and 500, we're able to capture all of the meaningful uh, vector vector attributes for a particular word, and then properly represent them. And then we have the dense feature. So there are no zero terms in these kind of word embeddings. So in the previous segment, in the distributional representation and the symbolic representation, there were a lot of zeros in the vocabulary corpus itself, right? So there is a lot of zeros in the numerical vector that represents the vocabulary corpus. So that was a major issue for us, and that created sparsity kind of scenario. But then here, most of the values, not most, all of the values in the word embeddings vector list will be a non-zero number. So it will be a decimal, and it could be negative or positive depending upon the word embeddings training and the word embeddings text corpus. Fine, data corpus. And then since they are very much lesser in terms of dimensionality, and then they are very much less in terms of sparsity, the computational efficiency is very much higher, and that is why they're very much efficient for machine learning tasks. And along with this, they capture even the relationships, like the semantic relationships. How so? Because they're distributed. They're distributed representations. Why so? Because for if you see, we'll see how they're trained, but then I'll give you a glimpse of how they're trained. In a sentence, a particular word, usually for distributional representation, we just take one word in consideration and then we do statistical analysis, right? Statistical counts, right? But then here, we take one sentence's word, we give out the responsibility for representing this word with the other words in the same sentence. And that is how it became a distributed representation. And that is how they're able to capture semantic relationships. Fine. Okay. So now we'll see. Yeah, this is the proper pictorial representation of how these word embeddings are properly representing that word. Fine. So these embeddings are learned from a large text corpus where the model predicts a word from its surrounding words. So to get the context, right? And vice versa. What is this vice versa? There are two different techniques in coming up with word embeddings. We'll look into it as well. One technique is like this, like get using the surrounding words to get the uh, middle word, and the other technique is using the middle word to create the surrounding words. So two different techniques so that the model is robust. So word embeddings mark the start of modern neural NLP because with this the representation became standardized. It was more robust. It was able to capture the semantic relationship between the words, and the machine learning models started performing better. The accuracy and the other metrics were actually much better than the previous techniques. And neural networks also, you can actually use word embeddings for both machine learning models as well as your neural networks. And in both the cases, the performance was very good. Fine. So, while discussing about this word embedding, it's very much important to know what is the industrial counterpart that used this particular word embeddings, and that would be our word to vec. So it was released by Google again. So you can actually search about the like you can see the research paper Mikolov et al. 2013. If you go to this, you'll be able to see the whole research paper. So if I have to give you a glimpse of how this works, I can just give you this example. So it is so robust that if you just give this inference like king minus man plus woman, it will understand that it is referring, this whole expression is referring to queen. So because of the semantic representation, like it's able to capture the actual meaning of the words, right? And that was the major, very, very much important, significant factor that really kept word to vec impactful. Fine. So it mapped the words to vectors such as the words with similar meanings are close together in the vector space. If we have already discussed this. Yeah. So if I have to give you a glimpse of how this word to vec works, so it takes in the word's initial vector form. That would be your distributional vector form in Vx, and then that would be uh, processed using hidden layers, and then again you'll be all of these words are actually represented, or even these vectors, these one not encoded vectors are actually mapped to the words, right? So these would be used in first input layer as well as the output layer, and the hidden layer is where the actual embeddings happens. So this is an example. So word direct learns word representation by analyzing a large text corpus and mapping words to vectors based on the context they appear. Fine. So this is a very, what to say, higher level description of word to vec. We'll go through each and every different stage of the layer in the word to vec architecture, and then we'll go and see how it really works out, really functions. Fine. Before going to the detailed architecture of word to vec, we'll move on to this pre-trained embedding. So you might actually have this doubt with you. So we have this word to vec model with us. So each one of us could actually go for our own word embeddings, right? So people around the world could actually come up with their own word embedding, and then the word embedding could become unstandardized. Like each person will have some different machine learning model, and the different machine learning or a deep learning model will work efficient only with their own word embedding, but then not others word embedding. That could become a serious um, what is it, a chaos in the ecosystem. And along with that, getting the most robust word embedding is very much difficult. So because it needs a lot of training, and the data required to train the whole word to vec model is large. It's huge. Only when the data is huge, and only when the text corpus used to train the model is huge. Only in that situation, your model will be robust and understand all types of relationships, meaningful relationships, and context of different words. How they are linked. How are they semantically related? Those kind of features would be mapped through the weights only when the model or the neural network is trained with large corpus. So that is why many of the big tech corporations actually release their own pre-trained word embeddings. And we have a lot of these. You can see Google has its own word2vec, and then Stanford came up with this glove, and then Facebook came with this fast text. And all of these come with various dimensions. You could have different variations, different dimensions of embeddings for different models itself. And they're all robust. You can actually use any one of them for your particular NLP task. Fine. So yes, so this was the one thing, and we'll just see an implementation of this pre-trained embedding, and then we'll move forward with the detailed architecture of what to make. Fine. So it is very much straightforward here. We have a library called as GenSim. So first you have to install GenSim in your Jupyter Notebook or in your Google Colab, and after that you have to import the models like the word2vec and the keyed vectors. And then we have the pre-trained path. So already the Google has actually trained their model, right? So we are getting the model through the binary file. So models are saved either in binary format or H5 format or TensorRT or ONNX. That kind of formats are there available. In the initial days, people usually went for binary format directly. But then whatever I told you, this TensorRT or this ONNX and then H5 format are more optimized for the hardware that they're using for the model. Fine. So yeah, so in this case, we're using a binary file. So this model is loaded. We take in the path, the file's path, and then we load the model. And then after the loading is done, we can get the vocab, and then we can directly use the model for getting the similarity score and then different things. We'll see this whole implementation in our Google Colab. Fine. So yeah, this is what you'll see. Actually, I've just shown it here, but then we'll run it out and then see it. Fine. Now we'll look on to the implementation of pre-trained embedding model. So first we install this NumPy 1.25.2 version. So we install it, and then it will ask you to restart the session. So you restart the kernel so that the kernel is configured for this particular version of NumPy. And then you need to install even GenSim. So you use pip install GenSim, and then you import GenSim. Fine. So after installing GenSim, you can directly go for this gensim.downloader. From this particular module, you import API function or API class. Inside that, you will call the load function. So through this API class, you'll be able to load any of the models. And here we have loaded the word2vec model, which is trained on the Google News, and it has 300 dimensions. Fine. So it'll take some lot of time because it is, if you see the number of MBs or GB, this is around 1.6 GB, more than 1.5. So it is a lot of GB. So you have to wait for some time after you're running this. So you have to wait for some time, and then you can directly use the model through this. You can directly get the vector is equal to model. So you'll get the vector form of this particular word in this form. So word2vec converts. So what we're doing is essentially initially, if you have to directly get the model, you load the model and then use something called as keyed vector. Keyed vector would not be the output of the model or the input of the model, but then it will be in between, because the word2vec would be trained differently. We'll get it in the architecture later. We'll just see the application now. Fine. So we get the vector representation of this word computer in this form. So you can see here, all of the numbers are non-zero and they're all decimal, and the number of dimensions is 10 here because we just printed it 10 up to like first 10 elements we printed out of the whole vector. But then if you print it properly, it will be around 300 elements. Fine. And then we can even use this function called the most similar. So model here is actually a class. So we create a model class. Inside that, there will be some variables or class variables or properties where the model's parameters would be stored. And whenever you call this particular most similar function, it use that at different attributes and then get this word and then get the top 5 similar words for this word king. So it'll give all of the words here. See, whichever is very much nearer to this king's vector space, it'll be showing you all of that. So these are actually similarity scores between the vectors of these words with the king word. Fine. And then you can do the same. Even it can give you proper analogy as well. So you can give it here like this: positive is equal to king and woman, negative is equal to man. And then top one recommend only one topmost result for this. So it'll give you the analogy for this result as this. So what are we doing here? King plus woman minus man will give you queen, right? So that's why it's positive and then it's negative connotation, and then you get the analogy result as queen. So yeah. And then if you see the similarity score between king and queen, you can see it here properly. So it's same as this, right? See, this is the similarity score between king and queen, and it was same as this. I hope now you understood. Okay. Now we have seen all of the vector forms in the numerical numbers. We'll look into the visual representation of these word embeddings using the library called as Plotly. So first you have to install Plotly, and then you use this particular code. So here we are using a metric or a technique called as TSNE. We'll look into what is this TSNE is in detail. You can even see it here. So distributed stochastic neighbor embedding. So we'll look into the detailed format of what is really happening behind the scenes with this. So, but then if you want to just know what is happening in this code, it is just converting all of the different 300 dimensional vector space of these words into 2-dimensional space. It's just converting them into 2-dimensional space and then storing it, and then we're just initiating this TSN here, and then here is where we're really transforming these vectors, whichever we got for these words. So you can get the vectors here through this um, comprehensive list comprehension technique. We can actually get the list of vectors for each and every word, and those will be converted into an array and an numpy array, and then will be given into the fit transform function inside this TSND class. Fine. So here this class is initiated by the constructor TSND with 2 components, meaning you have to reduce it to 2 dimensions. Fine. So we're reducing the 300 dimensional vector space into 2-dimensional vector space, and then perplexity is also one of the metrics. We'll see what is this and all clearly. Okay. Now we can just plot it out using the Plotly library. So before doing that, this will be in your vector form again. So you have to convert into, it'll be an array form. So it'll be an array form again. You have to convert into data frame, and then store columns. You have to label them, and then we can give the words. We can add this another column called words to the data frame, and then we can directly plot this data frame through the Plotly scatter function. So if we do that, this is the result that you'll get. Beautiful, isn't it? So you have your words properly, and you can even play hover on it, you'll get the value. So you can see here it's only 2-dimensional. That's why we have only 2-dimensional numbers. Only x and y value is here. But then how did it convert 300 numbers that is representing the words with only just 2 numbers? There is a technique for it. We'll look into it. So you can see here clearly those which are clearly near would have a similar meaning, and those which are further away will have a different meaning. So we can see it here. Fine. We look into a more detailed form of this TSNE representation as well for 50 word embeddings. Fine. So if there are 50 words, but then each of the words are grouped, like for our understanding, we just group them with some labels showcasing a domain of these words. But then if you just plot them, like all of these functions are very much straightforward. I'll be attaching the notebook in the description. You can go access it. But then if you follow through this whole code snippet, if you run it all, this is what you'll get. I'll just show you the result, and then I'll then explain you the code. Fine. So just see this. So all of those words which are having similar domains, domain knowledge or domain topic, they all came together. They're labeled with same color, and even through value, they're actually almost similar to each other. See, this is the distributional similarity, meaning the words which are used in the same context of a sentence are similar to each other. This is the perfect example of that. We got AI alone here. It shouldn't be here, but then we considered this word group, though we consider it as tech. This word in the word embeddings, it is considered as a island or something. Fine, and similar to even the Python. Python is considered as a like what is it, an animal or something like a. Actually, it is a vertebrate reptile, but then it comes under the Animalia class, so it could be considered as an animal, and that is why the vector space is much more closer to this. The word to vec did not understand that Python is a tech related word. So that is why it has went here. But then remaining things you can actually clearly see. All of the other words are coming closer to each other, and even the royal domain, the countries, the technology related stuff, all of those are actually coming together. Fine. So this is how you'll get the embeddings. So I hope you understood what these embeddings will look like. Fine. Okay, fine. Now we'll go to the coding part. Let's see this. So what are we doing here for each and every category? We are iterating through it, and then we are adding this categories list these many number of times with the number of counts we have for the in the word list. Word list would be your count here, right? So now those many number of times we're just adding this so that we're increasing the size of it, and then we'll add the category here. We'll add it and then we'll add this. So for each and every category, we do that. We're first initiating all of those different words and then we can do that. And we're getting the vector form for each and every word in the words list. And then we directly get this. It's again same thing on what I did previously. And then we make it into a data frame and then we plot it. I hope it is understood. Fine. Now we'll look into another implementation using glove, and then we'll go on to see what is this TSNE. Fine, stochastic neighbor embedding. We'll look into it. Before that, we'll just see what kind of implementation can be seen, what kind of output can be seen even using glove. So for implementation of glove, we used the Spacies model. So Spacy library has this encode web MD model, and this could be used for getting your glove representation of the words. So this glove, they've actually Spacies model is named as encode web MD, and this model is based on the glove algorithm, but then it is trained on common crowd data set. Fine. So now if you just plot or get the vector form for this particular sentence, Canada is a large country, then you'll get this. You'll get the whole sentence would be represented in terms of vector here. That is how glove works. So we look into it. We just see how this is looking, so you can have an idea of why it is called a dense and low dimensional vector space, because there are no zero numbers. Like there is no element with the value zero. It's either non-zero positive or non-zero negative, right? So that could be your elements for all the 300 elements in the vector space. Fine. Similarly, you can do it for even NLP. So what is this time? This actually tells you the time taken by the CPU to get this whole vector. So this microseconds. So imagine this. So we did the same even here also. You can get the same 700 microseconds. So okay, fine. But then you get the whole 300 dimensional vector space for this sentence. Fine. I don't know exactly how many dimensions are there for this glove based model. I'm just telling you as 300, but then I have to cross check it. But then for this, only for the glove model list, I have to cross check it. But then for the other word to vec, it's very much straightforward, man. We used 300 dimensional uh, word embeddings producing word to vec model. Here for cloud, we didn't see the architecture of Spacey because we are using a third party or a Spacey's model that is trained using the glove algorithm, right? So that is why we don't know exactly of how many dimensions are printed here. Maybe we can actually, if this is connected and if this is run properly from scratch, you can just, after this, you can just add this particular code and just check the dimensions. Len of vector. You'll get the size of it. Fine. I'm just saving this. I'm not going to run this. I'll be attaching this notebook in the video description, right? You can actually run it out and then check it. Fine. Fine. So now we'll move on to the next most important topic. We'll look into T, S, and E. So what is this T here? So T represents the statistic distribution called as T distribution. And that term is actually out of scope for this particular course because it is very much into statistic. There is Z distribution and T distribution. And then we have p-value distribution. All of that is there in statistic. If you're very much curious about that, please search about it and then get back. Fine. But then you won't be required to learn that here, actually. You just have to understand what is this used for, where can you use it, and then you have to understand how does it work. That is all you have to know. T distribution is a statistic distribution. That is all you have to know for now. But then I'll tell you how this distribution helps us with the equation. I'll just show you the equation and then tell you how this distribution is relevant for us and how is it being used here for reducing the dimensionality of higher dimensional word embeddings. Fine. So we'll see. So distributed stochastic neighbor embedding is the full form for this. So what is the meaning of stochastic here? Stochastic meaning any process or anything that is non-deterministic can be called as stochastic. It will be random or could say undeterministic. So it could be unpredictable. Sometimes it could be because this T distributed stochastic neighboring embedding can actually vary. The values that you get here. This is what I used here, right? I showed you a diagram here, right? Let me show you. So I showed you a diagram with these metrics, right? These values. Like all of the word embeddings had 300 dimensions, and they reduced it to just 2 dimensions here, X and Y. But then how are you getting these values? We use some formulae for this, and then we used even the cosine similarity kind of score out for this, and then we got this. But then if we see these values here, these values are not deterministic, meaning they're not predictable, they're not constant for this India. For each and every run of this particular model, this particular program, this TSNE will come up with a new numeric with respect to the other words in the whole data set. Now, in this particular case, since it is 50 words, these words are here. Now it has it has come up with these numbers 0.01979 for X value and Y value as minus 7.414 for India, for the word India. But then it could be different if you run it again. Fine. So that is why it's called stochastic instead of deterministic. Fine. So that is one thing that you have to know. Fine. So that is why we call it as actually a stochastic neighbor embedding. So what it does is it is mainly used for visualizing. And why are we even visualizing this? How can you even first of all visualize? If it is a higher dimensional number, you won't be able to plot it in 2 dimension. Even if you make it into a 3 dimensional thing, then it will become a 3 dimensional animation or something. But then even that one is very much difficult sometimes to render as a diagram or even understand it from the diagram. So 2D is what we usually use for visualizing the different embeddings. Fine. But then how do you represent the same higher dimensional numbers, higher dimensional vectors into only 2 dimensions? How do you do that? So that is where this comes into play. So what we do here is we project these vectors, 3 dimensional vectors in the space, and then this TSNE does not care about any other words which are far away from a particular word. For example, if you have to come up with the least possible representation for one particular word, what will I do? I'll take this word and look into it and then see what all words are nearby. So I'll make sure that the words which are nearby alone are properly maintained. The distance between these words which are nearby alone is properly maintained, or at least proportionally maintained. And then we'll reduce all of the higher dimension of 300 dimensions into 2 dimensions. It's like, almost like, imagine this. You have the whole earth as a globe, right? It's actually even not a proper sphere. It's a bulged sphere, bulged in the middle. So what do we do in the map with using a 2D dimensional map? What we do, we just proportionally make it into a two-dimensional representation, right? In a geographical map. Same thing happens with even TSNE. So what it does is it takes in a higher dimensional vector which has 300 dimensions. In reality, here the globe actually is of 3 dimensions. We make it into two dimension. Here we are making 3 dimension into 2 dimensions. So that is the only difference between a globe to map and the TSNE's work. Fine. So we reduce the dimensions by making sure that those neighbors are actually maintained properly. The closeness with the neighbors is maintained properly, but then the distant neighbors are not even cared for a particular word. But then the close neighbors are maintained properly and they are properly uh, reduced down to 2 dimensions. And even in the 2 dimension, we make sure that the neighbors are close to the word, whichever we are representing. Fine. So this is the advantage that TSNE does. Like this is an advantage, and this is the most important thing that TSNE does. And because of this, we are able to come up with an understanding by visualizing that okay, these similar words are properly maintained even in the higher space. Fine. So we might sometimes the word embeddings even in the higher space might be wrong, right? So how do you make sure that the word embeddings in the higher space is correct? By visualizing them. So we visualize them and then make sure okay, if the visualization comes out to be a 2D map with words with plotted nearby are not even meaningful enough to be closer, then we can say, okay, the word embeddings are not perfectly working. That is why TSN is showing this. So how can I improve it further? So this became an evaluation metric. TSNE became an evaluation metric for a word embeddings itself, so that we know how well is a word embedding representing the particular word and the other words which are in the same domain, and how well it is differentiating between different words from different domains of two words from different domains. How well does it differentiate between those? How well is the word embedding differentiating between those, and how well is it properly understood by the word to vec or any word embedding neural network? Fine. So this is the most important thing, and they are used even for image features. So for both image features and word vectors, we can actually use TSNE. So what are the main goals of TSNE? Reduce high dimensional data from 3 dimensional word vectors to 2 dimensional or 3 dimensional. It could be even 3 dimension, and then preserve the local structure. So that is why I told you all the neighbors are actually properly maintained. Like even if you see a map, a 2D map, a geographical map, all of the countries which are nearby will be properly shaped and they'll be in proper proportion, like how they are in the reality. That is what they are doing even with this. So preserve local structure. So the points that are close in higher dimension should remain close in the low dimensional visualization. And then create clusters that visually reveal semantic or structural relationship. So yes, so we saw this particular representation, right? Here we saw this clusters of words. We didn't actually plan to make this, but then the word embeddings, whichever we got naturally from this word to vec metrics, it automatically had closer vector numbers representation in even in the higher space, and that is why TSNE was able, when it reduced all of the dimensions to just two. Even in that time, all of these different countries came together. You can even see why some of the words are not even properly represented. It actually it's a proof that okay, TSNE is working perfectly to make sure all of the higher dimensions are properly reduced to the two dimensional space. Fine. So this is also an example for it. Python, it got confused between whether Python is a technology or animal or something. Fine. So yeah. So so these are the main 3 goals: reduce high dimensional data and to a low dimensional data, and then preserve the local structure, and then create clusters that visually reveal semantic or structural relationship. Fine. So how does it do this? So it does this by first going out and computing probabilities that measure how similar each point of pair of point is. So Each pair of point meaning each word will be represented as a point, and that point would be of higher dimension, and we'll be comparing each and every element of that point's vector with the other word which is nearby. That words, that vectors, that first element, we'll be comparing the probability of how close it is, how similar they are. So for point xi, its similarity to xji, the xj is calculated using the Gaussian distribution. So there's majorly a statistical technique, Gaussian distribution. I hope you understand what Gaussian distribution is. So it's actually a curve of probability. It could be a normal bell curve is different, and the Gaussian distribution is different. And it's just a plot of probabilities for different statistic. Find that could be a Gaussian distribution. So we using this, it actually calculates the probability of how close they are using this formula properly. So it is a exponential e power all of that, and then we add e power all of this together, and then we get this good probability. Fine. So here Pji is the probability of j with I, and Pij is the probability of I with j. And then we divide it by 2 into n. N is the number of data points in the data set that is used for this, for getting this probability. Fine. So it depends upon the number of words and all, or number of data points. Fine. So we get this probability, and then what do? We make sure that this probability is maintained even for the lower dimension. So pairwise similarity in even lower dimension. So this was for high dimensional space. We get the probability of these different words in high dimension space first, and then map the data to a lower dimension and call these as yi. Compute similar pairwise similarities using students' T distribution. So heavy tailed distribution. It's called a students heavy tailed distribution. I hope it's actually a statistical notion again. Usually for any probability curve, there'll be some tails, some endpoints, extreme endpoints. Fine, for any population. It comes under statistics, man. It's out of scope. It will be a very large topic. It's out of scope from this course. You have to learn. If you're really curious about it, then learn it and then come back, or you can learn it afterwards. But then for now, just to know this. So why are we using this T distribution? To make sure that we avoid the crowding problem. So allow the moderate distances to spread out more clearly. So why did we usually in a probability curve? What happens? Most of the population's mean value will come in the higher, like, major chunk here. In the tail values, it be very the probability of these extreme values will be very much small. And that is why when we take these probabilities alone, we make sure that all the like the representation, the probability representation, and the reduction to two dimension is very much clear and distinct. So the similar words which are having closer vector space would be discrete, will be made sure to be very much together, and they're very much separated from the other ones which are not closer. So that is why we, to avoid the crowding problem, we did this. Fine. So if you're not understanding this, don't worry. It is not a major thing. I'm just explaining this mathematics so that it's more comprehensive for students who are very much into even mathematics. Fine. And then we minimize the difference between the distributions. Which distributions? We minimize the difference between this distribution and this particular high dimension distribution. Why are we doing this? So that we make sure that the neighbors are properly embedded, the neighbors are properly represented. And we use this Kullback Leibler divergence to measure how different the high dimensional and low dimensional distributions are using log of these two different probabilities, and then use gradient descent to minimize this cost by adjusting the 2D, 3D positions. So I'll show you how this properly works in a graphical representation. Fine, I'll tell you this. Okay, I'll show you. I'll show it to you now itself. It'll be easier for you to understand. So what did we do here? This was the two dimensional representation that we got initially. Okay, the step 0. We did not even go for gradient descent. So we just plotted the we did our transformation function and then reduced the high dimensional space into low dimensional space, and then we got this plot. Fine, we got this plot which is not very much clear. So now what do? We get the pairwise similarity of higher dimension, that is your pji and pij together, and then almost a mean of it, and then do the same for each and every word for lower dimension that we have plotted in our 2D space. And then we get the difference between them using this particular divergence loss, and then use this for our gradient descent and then minimize the cost. So then how are we, like, what are we doing here? We're doing exactly what we did for the neural networks. So using gradient descent, we improved the weight and then made the model learn the data more, right? Similarly, we use gradient descent to minimize the error, minimize the difference between the distribution, the high dimensional distributions similarity between their neighbors and the lower dimensional distributions similarity between the neighbors, and we reduce the difference between their distributions so that the two-dimensional space really represents the high dimensional space properly. Fine. With iterations. So we slowly do that. We don't just directly get that. We slowly improve it using gradient descent. So how do we do this? I'll just show you with this animation. So here's what it happens. So with iteration slowly, with step 1, step 2, step 3, and step 30, you slowly improve. You can see here, all of the closer things are going together. They're actually maintained together, and they're going away from the ones that are separate, that are very much different from them. Fine. You can see all of the different labeled data points are going together, and but then they maintaining their distance from their neighbors. That is the most important thing here. Fine. You see this? They came from here and then they're going away. This green is going away, pink is going away. All of these things are happening. So you can see it stepwise properly. So this is how your TSNE works. So initially it does some transformation and then reduces the high dimension to low dimension. But then the lower dimension will not be that optimized. It will be very much good with respect to its neighbors. But then the difference between its neighbors and the other words could be very much less because the transformation is not that clear. So what do? All of those neighboring neighboring words alone will be maintained, and they'll make sure that they're together and they're distinct from the other groups or clusters, and separate them properly so that we can visualize these different clusters clearly. And that is how TSNE is able to properly show you the high dimension to low dimension, and also make sure that the representation of high dimension is properly maintained in the low dimension. Only then it makes sense, right? Only then it's useful. TSNE is useful because it is able to represent the high dimension properly even in two dimension. If it is not able to do that, it will not be useful at all. So this is the most important aspect of TSNE. Fine. So now you understood why are we doing this and how it is done, I hope. Fine. I hope you understood this. Now you can see the key parameters in TSNE. So the first one is perplexity. Perplexity is a parameter. We'll see that in the code as well. So it controls the balance between the local and global structures. So the nearest neighbors. So nearest neighbors, how close should I be with the nearest neighbors, and how close should I be with the further neighbors or the global structure itself. Fine. This controls the balance. This parameter controls the balance of it. And then n iter is very much straightforward. Number of optimizations, number of steps should I do for improving the whole representation. And then learning rate and the number of steps during optimization of that learning step. And then random state is seed for reproducibility. So random state is you will see random state in every machine learning algorithm, every deep learning algorithm, everywhere. It is just a initializer. It's a random initializer, so that you can, any person who's again doing the same, implementing the same process or the algorithm from scratch, can use this random state, this particular specified random state, so that you can initialize in the same way as the research paper or the person who has already done this or who has already developed this. Fine. So that is your random state. So what are the limitations here? Computationally expensive for large data sets. That's a major limitation for TSNE and doesn't preserve global distances. I told you, right? It maintains the distance for neighbors, but then the global distances are not properly maintained because they have to represent the high dimension in low dimension. So it has to make justice with the low nearest neighbors and the further neighbors. So it on a short term goal, gives more. It gives actually more priority to the nearest neighbors, and then doesn't care about the farther neighbors. And that is why it's not able to preserve the global structure properly, global distance properly. Stochastic, so different results across runs. So that is why we use random state. So that is why I told you it's stochastic, and that is why we use random states. So initialization also matters because it is undeterministic. It is not it will not give the same result each and every time. These numbers that I told you will not be every time the same numbers. If you give the same words also, fine. The two-dimensional representations, and then doesn't generalize to new data. This is the most significant limitation. So it doesn't generalize to new data, and that is non-parametric nature. So these are limitations. Okay, fine. You saw the limitations. So when to use TSNE? Whenever you want to visualize the word embeddings, and whenever you want to visualize sentence and paragraph vectors or clusters in a data, it could be your images or audio, and even an NLP model outputs. Even your outputs of your NLP models can be visualized using this. Fine. So overall, TSND acts like trying to flatten a crumbled 3D paper map into 2D. Fine. And it tries to keep nearby cities closer, even if it means to distorting the far away ones. That is exactly what it is doing, man. So even clearly, even the geographical map also works the same way, right? It makes sure that the cities that are nearby are maintained properly in the map, but then it doesn't um, care about the cities or towns that are far away from the city, because that in that case, you won't be able to properly represent the nearby ones, and the precision of that will not be properly maintained. But then these far away objects need not be properly represented, but then we have the real structure itself. So we want to know which are nearby, and we want to know the overall structure, and then whether it is the nearby ones are maintained properly or not in our TSN's case, and that is why we use this kind of a technique. Fine. So here it is just an implementation. We used PSA to first uh, reduce the dimensions here. PCA, principal component analysis, based dimensionality reduction. We do that so that we simulate the TSNE spread and then we animated it. So that is how we got this. Fine. Okay, I hope you understood what TSNE is and what it does and how it works and all of that. Okay, then. Fine. With this, we wrap up this video. So till here, you saw the distributed representations and all of that. So we're wrapping up this video. So until here, you saw the distributed representation. We saw the terms that you have to know before getting into the distributed representation, like the distributional similarity and distributional hypothesis and many others. And then we saw why is this distributed representation needed? How does it work? What does it do? And then we implemented the pre-trained word embeddings using the Word2Vec and Glove library. Glove is from Meta, Word2Vec is from Google. Sorry, Glove is from Stanford and Word2Vec is from Google. And then we saw how to visualize the embeddings using TSNE. And then we saw what is this TSNE, how does it work, what does it do, and then how to implement this TSNE. Fine. So now we'll go to the as usual ritual of showcasing what really is needed from you. The starting is easy. Completing the minimum number of videos is easy, but then completing the whole series is very much challenging. Fine, it's not undoable. It's not difficult. It is challenging. That's the difference. So completing is challenging. Only the 5% had achieved it. I hope you are that 5%, and for that, you'll have to answer this question: are you going to be that or not? So you decided. I'm not going to say anything further than this. Fine. So yeah, next, as usual, make sure that you're disciplined and consistent in your efforts for completing the course and the whole series. And make sure that you get the whole knowledge, comprehensive knowledge. Fine? Fine. In the next video, we'll continue with the detailed description of the word-to-vec model's architecture. How is it even processing the information and making it into a vector form? We'll look into it in detail. Fine. And then we'll even implement the whole architecture, and then we'll implement with that implementation you'll be in a position to train your own word embedding. Fine. So with the next video you'll be able to train your own word embedding, and you'll become an expert in this conversion of words to numbers kind of sector or domain. Fine. So yes, so with that we wrap up this video. See you in the next video then. Have a nice day. Until then.